Okay, I was just gonna get some pre-shots here of stuff that's actually working. And of course, you and the... Oh, how nice. Very good.
Talk about efficiency now. Yeah. But it's not getting too cold on the top. So okay, we're going to have.
Oh, you know what? There must be enough clearance that goes around it.
Okay.
The air actually flows around to the other side.
But we'd like to have those available. Sort of put these all together there for last year's news. Do you remember? Vladimir, would you be a judge? Give an example.
Yeah.
I wonder what, hey, Yossi, what do you think would happen if you heat up the generator a little bit? Yeah, it goes down. You've been elected, Yossi.
I'm not saying. Just explain, man. Just explain.
I'd rather get it right.
It's hard. We tried it though.
Okay, who's going to be the presenter for the 4 Aces?
Yossi and, sorry.
Whichever one doesn't have a lot of responsibility for making it around.
So you. Oh, okay, I'll see. We basically, this is an alpha engine. We're the 4 Aces. We have reworked an alpha engine that was done maybe, I think it was 2 quarters ago. They seized up that one because they had much more, a much bigger heater and a much bigger, what we call dead volume area, space. And we've reduced that. We've added a regenerator in there, some steel wool in the line to function as a regenerator. We've added the heat transfer of this, of the water flow, ice water. And we remachined the new cylinders. We tried to redesign the whole crank system. Instead of having it stick out so much, we wanted to kind of bore it in and stick the shaft in there. More of a, but I had a real tough time getting the machine tolerances down to what I needed. I couldn't afford to lose this cold cylinder because it had such good tolerances, and I couldn't make a hot one as good, and I couldn't afford to take that one out of the line. So we left the same design, even though I don't think it's very good. What else? That's pretty much all we've done. No, that's not true. We redesigned some of the crank as far as, I think before you had just a cotter pin holding them in.
Yeah.
And we got roll pins that we tapped in there, and the shafts slide on, and they're locked in place with little wheel collars.
We followed the standard theoretical procedures that you would use in order to, at least on paper, succeed in promoting a greater temperature difference as well as better efficiency for regeneration. So that's always the first place to start, and it's always the best place to start. The practical applications of those are there. Cooling, regeneration, as well as smoother running bearings. Our bearing assembly was a little sloppy.
Yes, they are.
Are you willing to destroy another hot piston?
To get it running, yes.
Right, I'm going to make sure I don't point it at one exact spot.
That's from experience.
How's it been?
Careful, those propane torches get
No
hot.
burning hair.
It's all?
One of them was funny. Yeah, I think you guys have missed it. Basically, this coffee can engine.
Talk that way, probably, because there's a lot of people behind you, too.
Basically, this engine was designed for the high school demonstration. So, yes, it's not the sophisticated engine. It's basically made of wood and scrap coffee cans. And first, we had some problem with. We found some problem with the shaft and the bearings. It had two ball bearings on the shaft support. It didn't have a tight fit on the shaft. It was just loosely it. So we used the super glue to secure it. And to the bearing mounting, we used the super glue again to secure the outside bearing. And then we achieved a smooth running shaft, but see, without the water, it runs very smoothly. So with the water, the water, friction of the water, and just cannot run it that fast. This engine was designed to run at 20 to 30 RPM. When we got it to run, it only ran about 25 to, and maximum was 30, 35 RPM. The other problem was that this rod was keep touching this reel, so we had to.
Oh, you gonna demonstrate it at a high school? Was
The
that?
professor asked for this engine to be a high school presentation purpose. That's why we added this bar, just to prevent it from burning.
Do you have any,
The supercharger, you take a straw of the flexible kind, you make a U at the end, put it in there, and you go like this, like that charger, that'll make it run. Supercharger. No, you need one that goes right inside. Okay, flexible straw.
I just might mention, first of all, I think I've introduced him to many of you. Dr. Ted Finkelstein, who is very prominent in the Stirling engine community. You know Peter Taylor, I'm sure, and this is his design that he published in Scientific American about 8 or 10 years ago. So, it does work. It looks like it stops itself.
us to save energy.
Our group is Piston Power. That's the name of the team. My name is Wilson Fishman. Colleague Sujin, Ray, Evan, and Sergio. We came up with actually our new product. Well, it's a new design, and it's not running because it's not finished yet. But the way it works is this is the hot end of the machine or of the engine, and there's a displacer in here, which displaces the air from hot to cold on one side, and it also sends it through this chamber here, sends it to the power piston, which is on this side. And that was supposed to be driven. If you can see here, there's a hole offset from the center. That's supposed to be driven by those holes, and there's another flywheel also on this side. One on each side. That's to compensate. I mean, that's to put some inertia, so it drives the piston. And also we put to use more power. I mean, to use more, make it more efficient. We were going to put a propeller inside, that rotary, that was going to be driven by the fluid, by the motion of the fluid inside. So that will help drive the wheels also. So that's actually the design. And these pipes are connected here. Well, this is in the center. Goes through here, and then comes out of here, and then goes in here. That's how the cold lengths.
Okay, now where do you heat it?
Here.
You heat the
This is the displacer. It's sort of a. It's supposed to be a gamma engine, I think, and.
But it's hybrid. I think it's a more
Hybrid.
cross between gamma and rotary engine.
No,
That we've seen in the Japanese university. What happened is the rotary blade, we have to discard it before we come over here. It just falling apart. We need to get a more rigid material for that. So far, we have a stainless steel piston that was donated to us by one of the brake suppliers. We use a brake wheel cylinder, the pistons for the wheels for the disc for the caliper. But we use those things for the piston. We just go ahead and use aluminum for the cylinder itself, so it will be easier to machine and things like that. I imagine this thing will be run quite well, if it's to be complete with all the parts and things like that. Because I think we get more efficiency with this rotary action here, from the working fluid going back and forth.
The only problem we had with this engine is the due date was too close to when we started developing it.
Lance Cullen, Raj Chakshi, and Ronald Tam, our group members. We chose to design and build a rhombic drive Stirling engine. One of the most difficult parts of this engine is to design the rhombic mechanism, which is this lower part that you hear. The rhombic mechanism is made up of the links and the two yokes that you see here. This upper yoke and the lower yoke drive the piston and the displacer, which is located inside this cylinder right here. One of the problems that we're having right now, I think it's mainly fine-tuning. The tolerances with the piston, the displacer, and the cylinder are there. The tolerances for the links are there, but I think the main problem that we're having with this engine right now is the distance between the gears, which we're not able to fix right now because of a minor filing problem in the aluminum base in this base right here. Overall, I think we've spent too much time on this engine. For the last 2 weeks, none of us have been home later than 2 o'clock because of this baby right here. We almost got it to work. this morning. One of the reasons we thought it wasn't working was because of dead volume. We experimented with that by placing larger tubes, 1/2 inch diameter, the heating coils right here. We experimented with that, it didn't work. Next we thought it might have been a compression problem, but after discussing it with Professor Stein, it seems that our compression ratio and everything is correct. The only problem that we're having is just filing the base right, and I think once we correct that, this engine will run. See, in order for this engine to work perfectly, the yokes, the links, the piston, and the displacer have to be completely aligned with the cylinder. And right now, we're having a problem just getting everything to turn. The way the project was broken up, all 4 of us were given a certain task. Lance and I designed and built the cylinder right here. The yokes and the links were built mainly by Raj. The base and the outer housing were built by Ronald Tam. The gears, the extra inertia plates, and the piping and everything was a combined effort. Overall, it was a very team collaborated project. We all learned a lot. And if you have any questions, please feel free to ask.
Yeah, I'd like to see you rotate that around 360 degrees so that people on this side could see and then do it on the other side.
Okay.
And explain what's the top link and the bottom link, what they're doing. And while they're doing that, you might notice the coffee. Midnight somewhere.
Is it like a 1 engine working per class Jinx or something? Yeah, it used to be, right?
What we have here is 2 pistons, a displacer piston and a power piston. And we'll start with it at top dead center for the displacer piston. It's going to happen right here. So, as this is heated, the air expands, pushes this displacer piston down. That's when we get the power stroke out. So now all the air has gone through, compressed through here, through, and all being heated. It's all being heated. So now through the inertia, which is what we're trying to add to make it go around, it will start to rise again. And then this area will compress, therefore pushing the air back up through here,
which goes through the cooler. The cooler is actually cooled by water. There's a tube running through this cylinder right here with water flowing through it. And once the air is pushed through this cooler, it's sent back into the displacer part section. The fluid is now above the displacer.
and there's a seal right here to prevent the air between these two from going down below here. We want to be compressing this to push it through all these pipes. So I think the main problem here is the inertia, and we have too much friction going on.
In a more simple way of explaining this, when the air is in above the displacer, it's heated and therefore expands. This expanded air will flow through the tubes and into the power piston section, creating a power stroke. The inertia of the wheels is supposed to push the piston back up, forcing the air back into the displacer area, and thus repeating the cycle, making it continuous.
We did have it run pretty smoothly.
is another midnight engine that likes to run.
Don't worry about that. That's having the engine. It's a kit engine, originally given to us by Sandias Lab. They built. They came with a pretty much. Here's the design you put together, and they had the machinists put it together. He did such a fine job on it that they couldn't run it. So we got the engine, we tore it apart, we cleaned it up, we found what was wrong with it, and what it was the power, the heat cylinder. When they put it together, and we made it run. On this side, it's the cold side. And it's cooled by water. There's a set of heat exchanger. There's a small heat exchanger right here on the space plate, and the working fluid moves from the power piston to the cold piston and starts the cycle. When this one's going, the temperature was about 700 degrees, unfortunately. But what we're trying to do next, after we get this, prove this runs, we're going to take it apart and see how to reverse the drive in such that we can make it. You promise. Now, what happens is we have a large mass we've got to heat up, so that's the cylinder is a stainless steel, so it takes a little bit to heat up the mass. And don't worry about the thermocouple wire; it was chosen that way because it could resist this heat. I tried to melt it with.
Really electric motor?
I think we got it here.
Right.
I think it's official.
Well, here's a demonstration of the Stirling cycle. Put heat in, you got a cold. Province. Right now the cold cylinder is at 87 degrees, and the hot cylinder is 940 now.
Whoa. What do you do in the case of a tie? For no run.
I recognize that you guys have chosen a subject which is a tough job because Stirling engines is most interesting in engineering, but very unrewarding as far as technology up to date is concerned. There have always been high hopes, but very little fulfillment of those hopes. And it's a terrific subject for academic endeavor in that there are a lot of questions that need to be solved. And continually over the year one finds new aspects, new characteristics that improve the engine no end. So that there are a couple of features which are so obvious to anybody who understands some engineering. For example, the fact that the efficiency is clearly superior to any other engine. And not only theoretically, but it can be proven. Excellent engines have been built, engines that exceed the efficiency of diesel engines, which is perhaps the most practical, smaller power generator that we have. And the field is wide open. And the arguments that I get into is mostly over application. The commercial success is just about around the corner. Lately there has been an effort to, for example, apply cryogenically to computers, and it would have been a great hit had computer chip development not taken another turn so that the cooling of the chip was not commercially viable, even though the Stirling engines now can do it real well. But there are other things in the offing. The efforts that you guys have made is terrific. It is, if I may venture a little bit of a criticism, I haven't seen any free piston designs. And free piston designs are particularly good for student efforts because they're easier to build. And they're also kind of challenging technically. So maybe after this, maybe some of you might get together and design some good free piston machines. They're easy to build. And in any event, the technology of small power producers is shifting now from kinematic machines to free piston machines. So pass that through your program.
Figuring out about the best looking engine, the best working engine, and the most interesting. Okay, and so for the best looking or most aesthetic engine, the winner for that was Piston Power. A prize, and you might want to open the prize right now.
Hey guys.
Engine, best operating engine is sterling silver. The prize. So you might want to open that. And then finally, the most technically challenging or the most interesting engine. And that most interesting, and that prize goes to Strangebrew. And so, all of you, with your certificate of accomplishment and your prize. You can guess what half of it is.
Before we open this, Strangebrew would like to thank Professor Stover as well as the Formula Race Car team for letting us use the machines and the tools that we needed to complete our engine. And Professor Stein for his time in helping us design it. And there's
And I'll pass it. Dr. Finkelstein for coming. And I'd like to invite all of you to, we have a few things around. We have the parts for the 495 engine. Those of you not in the class, ask somebody in the class to explain what you're looking at. We also have a video on a very new Stirling engine, the Stirling engine that has been chosen by General Motors to be their primary engine in their hybrid electric vehicle. That's the Stirling Thermal Motors 4120 engine. So it may be that you'll be able to buy an automobile within the next 3 or 4 years with a Stirling engine as the regenerator or the generator system for a hybrid electric vehicle. So if you want to look at the video, it also explains how Stirling engine works. So we've all seen it, but anybody would like to, I'll start it in just a minute.